Not much better. Stop share for a second. Okay, and everybody hear me out there?
Yes.
Good, I can hear you. Good. Hang on for a second. All right, so today what we're going to do is we're going to talk about least squares. So today is, I believe, the 2nd. And again, this is Math 3300. Okay, so we'll talk about projections and the method of least squares. All right, so let me kind of give you the idea of how this works. So we need to go back to the first part of the class where we're looking at systems of equations. So consider the system of equations. Namely, we have AX equals B. Now, we know that this system sometimes has a solution and sometimes does not have a solution. So sometimes this is inconsistent. All right. Now, what I'd like to do is I'd like to sort of kind of give you a picture why this system could be inconsistent, right? So one thing to think about is the following. So let me just draw you this picture. So this picture down here is going to be the column space of A. All right, so the column space basically gives you the range of A or what the image of A is. So this is the image of A under the linear transformation. So this system is consistent if B lies in the column space. Okay. So the system AX equals B is consistent if and only if B is in the column space of A. Okay. All right, so suppose I have like vectors which are in the column space like this. Let's call them A1 and A2. Okay. Now, if B is inconsistent, or the AX equals B is inconsistent, then the B vector here will lie outside. Okay, so it's going to be outside the column space. And so what you can ask yourself is there what is the best possible solution? So what's the solution that's going to be the closest to B? And we know the answer to that. The answer is just when you project down to the column space and then you take the projection formula and you get the projection of B onto the column space. All right, so let me state that a little bit more clearly. So the idea is the following. So we're going to find values, let's call them X bar, such that the error which is equal to AX minus B, is minimized. Okay, so you want the error between the distance between the column space and B to be as small as possible. Okay, so that occurs in this when you project down orthogonally. All right. Okay, now if AX equals B is consistent, then E is equal to 0. So if AX equals B is consistent, then you don't have to worry about anything. E is actually equal to 0. Okay, so let's assume that B is actually not in the column space. Okay. Now, we just need to make a little bit of an observation. So down here is something of the form AX over here, okay? And we know that AX is minimized, or the error is minimized, if AX is actually perpendicular to the column space, or AX minus B is perpendicular to the column space. So note the error E is minimized, okay, if AX minus B, so this is AX minus B over here. So if this vector here is perpendicular to the column space. All right. Okay, now let me just kind of argue this through next. So observe that the row space of A is perpendicular to the null space of A. So the row space of A is just the rows of A, the span of the rows of A. And so when I take the dot product of the rows of A with something in the null space, I get 0. Okay. So since the column space is just sort of the transpose of A, that means that the column space is perpendicular to the null space of A transpose. So therefore, the column space of A is perpendicular to the null space of the transpose of A. Okay. So if we want to minimize the error, we have AX minus B is perpendicular to the column space. So if the error is minimized, then AX minus B must be in the null space of A transpose. So consequently, AX minus B is in the null space of A transpose. Okay. So what does that mean? It means that when I take A transpose times this vector, I get 0. So I get A transpose AX minus B has to be 0. Okay. And now you just sort of bring everything, you just multiply the A transpose all the way through. So we have A transpose AX must be equal to A transpose B. Okay. So this is when X is minimized, or when X minimizes the error. Okay, so this is an important formula to remember. Okay. All right, so now what I want to do is I want to somehow invert A transpose A. All right, so I want to find conditions on when I could take A transpose at A and I can invert it. So let's just kind of go over this for a second. So let's say A is a M by N matrix. Okay. So A transpose is an N by N matrix. So that means that A transpose A is a square matrix. So this is an M by N matrix. So it makes sense to actually try to find the inverse or see whether A transpose A is actually invertible or not. Okay, any questions up until this point? All right, now, so what we'll do is we'll make the following observation. And the observation is when I take A transpose A and A, these have the same null space. So in other words, the homogeneous system of solutions is the same for both these matrices. Okay, so let's justify this. So suppose that AX is equal to 0. Okay, so something is in the null space, right? So that means that if I take A transpose times AX, this is equal to A transpose times 0, which is 0. So that means that the null space of A is contained inside the null space of A transpose A. Okay, so if I take something in the null space of A, it has to be inside the null space of A transpose times A. Okay, now conversely, suppose that I have something in the null space of A transpose A, right? So therefore, if I take X transpose A transpose A times X, that's also going to be equal to 0, okay? But this is the same as AX transpose AX equals 0. And so this is just the dot product. So that means if I take AX squared in terms of the length, I get 0. And so remember, the length of a vector is 0 if and only if the vector is 0. So that means that AX has to be 0. All right, and that this shows that the null space of A transpose A has to be contained in the null space of A. Okay, so this gives you a justification that the null space of A and A transpose A are the same. Okay, questions? All right, so now what we can do is we can just sort of give a condition on A to ensure the invertibility of A transpose A. So namely, if A has linearly independent columns, that means that the null spaces can be 0, and then the null space of A transpose A will be 0, and A transpose A will be invertible. Okay, so here's the line of reasoning. So I'll repeat this. So suppose, now let me put a little star here, okay? So suppose A has linearly independent columns, okay? So this means that the null space of A has to be 0, which implies the null space of A transpose A has to be 0. And this implies that A transpose A is invertible. Sorry, yeah, is invertible. Okay. All right, so under star, we can go back up to this equation over here, and we can actually invert. So if star holds, then our solution is unique. So this is going to become A transpose A inverse A transpose times B. All right. So this actually minimizes this X here is going to be a solution which minimizes the distance between B and AX. Okay. So what is the projection? So the projection is going to be equal to A times X. Okay, so remember this point is actually in the column space of A, right? And so this is sort of the closest point to B. And so I'll just multiply both sides. So I get A times A transpose A inverse A transpose times B. Okay. Now, you should compare this with so you should compare with the one-dimensional situation of a projection. So remember what the projection formula was. It was, well, it was basically this formula over here in one dimension. So let me see, A transpose. Okay, so let me just write it out this way. So we did this last time. So it was A transpose over A transpose A, and then we applied it to B. Okay, and this was the projection matrix here. So this was capital P, and this was the projection matrix. Okay, any questions on this?
Yeah, I have a question.
Okay, go ahead.
And the star,
Yeah.
the star thing above, how did you get from the second to the third step?
Oh, up here? You
Yeah.
mean from here to here?
Yep. Or from null of A transpose A equals 0 to A transpose A is invertible.
Okay, so if you take the null space of A transpose A being 0, that means that, remember, A transpose A is going to be a square matrix.
Yeah.
Okay. So if the null space is actually equal to 0, that means that the columns are linearly independent.
Okay.
And there are n of them. And so they have to form a basis actually because there are n of them and the space is n dimensional.
So that also means that the determinant's not 0.
Right. The determinant's not 0.
Okay, thanks.
Okay. But it's a fact that it is actually a square matrix that allows you to say that.
Okay, I got it.
Got it? Okay. Sorry, I may have glossed over that a little bit. So thanks for bringing that up.
Dr. Nakano, what's
Yeah.
that word next to one dimensional? Is that
Oh, situation?
situation? Okay, thank
Yeah.
you.
Yeah. So last time what we did was we looked at the one-dimensional projection matrix, when you're just projecting a vector onto a line. And I just want to show you that in that case, the matrix is a 1-by-1 matrix. And so you can actually slide the A and the A transpose over, but if you have more than like a 1-by-1 matrix, you can't do that. And so this is the actual formula here, where you have to keep the A transpose A in the center and then invert it. Does that make sense?
Okay, I see. Thank you.
Yeah, the matrix multiplication is not commutative, so that's why we have to have a slightly more general formula for m by n matrices. Okay. All right, so we'll do some examples of this. I think it's kind of neat because we can actually find the closest points, and we could actually do a little bit of data analysis too. Okay, so let's actually do an example with some numbers. Okay, so the problem is to solve AX equals B by what are called least squares. Okay, so least squares is this method that I mentioned before. So i.e. use the formulas above. Okay. All right. Now I have to give you what A and B are. So the matrix A is just the matrix 1, 0, 1, 0, 1, 1. And matrix B is the vector 1, 1, 0. Okay, and notice that A, you can easily see, has linearly independent columns because the vector 0, 1, 1 does not lie on the line generated by 1, 0, 1. Okay, so note A has linearly independent columns. Okay. All right, so we can actually use the formula to solve for X. So let's write out the formula again. So least squares implies that the solution X will be given by A transpose A inverse times A transpose B. Okay. All right, so all we have to do is we just have to perform these matrix operations, and voila, we get the solution. All right, so first of all, let's take A transpose A. Okay, so we transpose this, we get 1, 0, 1, and we get 0, 1, 1. Okay, that's the transpose. And the matrix A is like that. Okay, so we should get a 2-by-2 matrix at the end, right? So I take the first row of A transpose and I dot it times the columns of A. So I get 2. So 101 dot 101 is 2. And then the next one I get is a 1, right? And then I get a 1, and then I get a 2. Okay, everyone all right with that? All right. Now let's just take the inverse of this. This is a 2-by-2 matrix. So what is the determinant going to be? It's going to be 4 minus 1. So 1/3. And then what do? We flip the A and the D and we negate the B and the C, right? So that's 2, 2, minus 1, minus 1. Okay, is everyone all right by that? This is the 2-by-2 formula for the inverse. Good. All right, so now what we have to do is we just have to matrix multiply everything out. So X, well, we have A transpose A inverse. That's going to be 1/3 of 2 minus 1 minus 1, 2. A transpose we have already. That's 1, 0, 1, 0, 1, 1. And B here is just 1, 0, 1, 0. Okay. So this is 1/3, 2 minus 1 minus 1, 2. And then I'm going to just multiply these two matrices first. Okay. And so what do we get? We get 1, 1. All right. And then let's multiply everything out. So I get 1/3. And what do I get? I get 2 minus 1, that's a 1. And I get minus 1 plus 2, that's a 1, 2, right? So the answer is 1/3, 1/3. Okay, so that's my x that I want. And then if I want to look at the point P, this is going to be a times x, right? And let's make sure, what was A? A was going to be 1, 0, 0, 1, 1, 1. So let's multiply that times 1/3, 1/3, and see what we get. Okay, so we should get something, of course, in the column space of A. So let's see what we get. Okay, so I get 1/3, 1/3, and 2/3. All right. Are there any questions on this problem? Yes, no?
I had a question at the very start. How can you explain again how we knew A was linearly independent without?
Oh, the columns?
Yeah,
Because
the
you only have 2 columns. And so if they're not, that means that the vector has to be, one vector has to be a linear combination of the other vector. Right? So they would have to lie on the same line.
Gotcha. Okay.
Got it? Okay, good. So with 2 vectors, it's really easy because you could just check whether, they're on the same line or not. If they're not on the same line, they're not linearly, they're linearly independent. Okay, other questions on this? All right. Now, let me just mention that just like the one-dimensional situation, the projection matrix here, so I had this projection matrix up here, which I'm going to label in a second. So I'm talking about this one up here. This projection matrix actually has rank 1, and also it's idempotent. Okay. Actually, I'll just say it's symmetric. It doesn't have rank 1. Okay. So let me just talk about projection matrices really quick. Okay, so here P is going to be equal to A times A transpose A inverse times A transpose. And if you work this out, this is the n by n matrix. Okay. And so here are the properties. One, P is idempotent. So if I project twice, it's the same as applying P once. So basically, if I project, I get down to the column space. Since I'm in the column space, if I project again, I don't go anywhere. Okay. And then 2, it turns out that P is a symmetric matrix. And 3, if I take the rank of P, that's going to be equal to the dimension of the column space of A, which is the same as the rank of A. I think I use small letters for rank here, so let me just do that. Oops. Okay. Ooh. Here we go. They updated my iPad, and now I don't know where all the commands are anymore. Okay. All right, good. Okay, any questions on these projection? Think of this as a projection matrix. All right. So in the time remaining, what I'd like to do is I'd like to talk about fitting data. And then what I'll do is I'll set everything up, and probably next time at the beginning of class, we'll actually do an example where we use these formulas. So this is called least squares fitting of data. All right. So here's the idea. So I'm going to just draw you a two-dimensional picture here. So I have a variable t, and then I have a variable r. And r is going to depend on t, just like, when y is dependent on x. And what I'm going to do is I'm going to have all these points that are plotted. So let me just kind of draw them in a slightly different color. Now let's do the green color. So I have a bunch of points. They're all over the place. I may have an outlier over here. So you can imagine you have this data set which looks something like this. Okay. All right. So you have this big data set. Now, what I'd like to do is I'd like to fit a line or find a line which best fits the data. Okay. So I want to find a line. Okay. That best fits the data. Okay. All right. So so I have my points. So let me kind of give you the points. So the points will be like T1. Oops. Sorry. Okay. So the points will be like T1, B1, T2, B2. Let's say TM, BM. Okay, so these are the points which are sort of in the green here. And what I'd like to do is I'd like to fit them with the line, right? So this line here, let's say is R is equal to C plus DT, all right? So let's just write out the equations that these points, would actually have to satisfy. So I'd have like C plus D T1 is equal to B1. That's one equation. C plus D T2 times B2. That would be another equation. And then down to C plus D Tn. Is that Tn or Tm? Tm is equal to Bm. Okay, so that would be another equation over there, like that. All right, so we have a system of equations. And, most likely this system, unless all these points lie on the same line, is going to be inconsistent. So what I'd like to do is I'd like to find C and D, which are the best fit. All right, so in order to do that, we transform this as follows. So we have a system of equations with 1 T1, 1 T2, 1 Tm, and CD here. And that's going to be equal to B1, B2, up to BM. All right, so you have a system of equations here, and you want to solve for C and D or find C and D, which provide the best fit for this data. So find the vector CD that provides the best solution. And we sort of know how to do that because we have the least squares method. Okay. All right, so let me do a little bit of labeling here. So this matrix here is A, and this matrix here is B. Okay, and this is your X. And now what we can do is we could just apply the least squares method to find C and D. Okay, so apply the least squares. All right, so let's do that. Okay, so so what do we have? We have that A transpose times A X is equal to A transpose times B. Okay. And now what I'm going to do is I'm just going to write out the matrices A transpose A and A transpose B, and then we'll see what we get. And once we do that, we'll sort of set things up to actually work on, various applications. Okay. All right, so this equation has to be satisfied, right? Okay, so now let's first of all compute A transpose A out. So that's 1, 1, T1 up to Tm. And then I have the ones down here, T1 up to Tm. Okay. So I just get a 2 by 2 matrix, and let's just compute that out. Okay. So the first thing is I get the dot product with the vector of ones and another vector of ones. There are m of them. So the first component is just m. Okay. The second one is just the sum of the TIs. Okay, where I ranges from 1 up to m. The second one is also the sum of the TIs too. When I take the dot product of the second row here with the first column of A. And then the last one is just the sum of the TI squareds. Okay, that's not so bad. And now let's take A transpose B. Okay, so A transpose B, I get the ones over here. I get the T1 up to Tm. And then I'm going to dot it with B1 up to Bm. Okay. So I get a vector, which is the sum of the B's. And then I get the sum of the TIs with the B's. Okay. All right, so let me give you the executive summary now. So this is the executive all right, so given points T1, B1, T2, B2, up to TMBM, okay? The straight line I don't know if you want to call it R. So say R equals C plus DT that minimizes the distance between the points and the line. Okay, so in other words, it's the line which sort of best fits this data, and it has to satisfy the following. So I have to have the following equation satisfied. So I have the M over here. So I'm just writing out A transpose A. The sum of the TIs over here, and the sum of the TI squareds times CD. And that's going to have to be equal to the sum of the BIs and the sum of the BIs and TIs. All right. So, given the input, we can actually solve for this. And if the matrix, so let me just write these out. So remember, this was A transpose A, and this was going to be the matrix A transpose B. Okay. All right. So given this setup, as long as we know that we can invert A transpose A, so there are conditions, there are situations where we can actually find the inverse of this 2x2 matrix. We can invert it, and then we could actually solve for C and D, and there's a unique solution. Okay, any questions on this? Okay, so let's see. I am not sure if I'm going to have time to do the example. So I'd rather not start the example and sort of keep you like overtime. So let me ask, are there any questions on least squares? The idea of least squares, how we actually derive the solutions for least squares? Questions?
Just
Go
a
ahead.
conceptual question. The point of least squares is just to find a solution that exists in the column space, or the closest thing to B, right? That exists in the column space.
That's right. So let me go back to the picture. Okay, so your system could be inconsistent, right? But maybe there's the best solution possible. And the best solution possible is the one which minimizes the distance from the vector B to the column space. Okay. And so you want to find a vector in the column space which actually minimizes this, the distance here. And
So it's almost like a regression formula, right?
yeah, I think it's definitely related to that. Yes.
Okay.
Yeah, least squares and regression are definitely related. So, yeah.
Does this only work with straight lines, or can you do curves?
Oh, that's a very good question. So I think we're going to do some examples later on where we actually do curves.
Okay, cool.
Yeah. Yeah, probably on Friday we'll do a little bit more sophisticated version of least squares. Okay, other questions? So on Friday, I'll actually do an example where we apply this with some numbers and an example using Hooke's law for springs. And then we'll go into a little bit more sophisticated way to do least squares. And that'll sort of finish the class out in terms of the material. If there's any sort of leftover material on Friday, I'll definitely be able to finish it up on Monday fairly quickly. And then we'll actually start in on a review for the class. So by Monday, please, if you have any questions about the content of the class, that's actually the time to ask. And we can actually go over things, and I'll actually have a set review, but maybe I'll leave like 5 or so minutes at the end of class for general questions on the material. Okay. Questions? Okay, so
one more
go ahead.
question about just the final exam. So obviously it's cumulative, but is it going to be evenly spaced out in terms of content covering all 3 exams, or is it going to be like more
I
heavily
think,
focused on what we recently talked about?
no, it's definitely going to be more evenly spaced out.
Okay.
Okay. That's actually better for you because you've had more time to absorb the material. And so that way, if it's completely weighted on the newest material, that means that, if you haven't had as much time to pick it up, then it could be a detriment in some sense. So I definitely want to give you some, a chance to actually show what you've, learned throughout the course. Yeah.
Gotcha.
And I'll definitely, I'm going to give you some ideas about what will be on the exam too, or what you need to know. I'm hoping that by now, that from the first 2 sets of reviews, it was pretty much, that was kind of the content of the test. Okay. And it'll be 10 problems, 20 points each. So the final will be worth 200 points, which is double the midterm, double one of the midterms. And so it makes the grade computation a lot, more straightforward. Okay, other questions? All right, so we will see you on Friday then, at the same time. Okay, see you then.